Hello, everyone. I am Michael from Math Together Canada, and I will explain how you can solve all of the final 5 questions on this year's AMC 12A. So let's start by problem 21. So you have this kind of like weird expression. Right away, you can notice that it's like inefficient to plug in values for A, K, and M. So let's do some simplification to this expression. So right away, you can factor out 4 to the A, and you'll get 1 plus 4 to the power of k plus and so on until 4 to the power of mk. And the bottom is just the same, except instead of 4 you have 2. So 4 to the a over 2 to the a is just 2 to the a. Now you have a partial sum of a geometric series, right? So this is 4 to the k. I'll use a different color, sorry. This is 4 to the k squared, and this is 4 to the power of k to the power of m, right? So it's 4 to the power of k to the power of 0 plus and so on. So right away, you can use the partial sum of a geometric series formula to get that it's equal to 4 to the power of m plus 1 times k minus 1 over, in the bottom, it's not 4 minus 1. A lot of people like wrote 4 minus 1 here and made the mistake and got stuck and like lost a lot of valuable time in the AMC. So it's 4 to the k minus 1 because the base is 4 to the k. And in the bottom, you can do the same thing. So it's 2 to the power of m plus 1 times k minus 1 over 2 to the k minus 1. Now you can move the denominator into the other side's numerator. So it's equal to 2 to the a times 2 to the k minus 1 over 4 to the k minus 1 times 4 to the power of m plus 1 k minus 1 over 2 to the power of m plus 1 k minus 1. Now notice 4 to the power of k minus 1, that's just 2 to the k squared minus 1. And you can factor out like something squared minus 1 as that thing minus 1 times that thing plus 1, right? So it's equal to 2 to the power of a times 2k minus 1 over 2k minus 1 times 2k plus 1 times, and you can do the same thing here again, right? 4 to the power of m plus 1k is just 2 to the power of m plus 1k squared. So you can factor it into 2 to the power of m plus 1k plus 1 times 2 to the power of m plus 1k minus 1 over 2 to the power of m plus 1k minus 1. Now, conveniently, these things cancel out. And notice it's all equal to 964. So now you can just move the denominator. You can get rid of all denominators and all fractions by moving this to the other side. So 964 times 2 to the power of k plus 1 is equal to 2 to the power of a times 2 to the power of m plus 1 k plus 1. And notice this is odd. This is also odd. That means 964 must be equal to like an odd number times the power of 2. And that power of 2, you can prime factorize it as 2 to the power of 2. So it's equal to 4 times 241 times 2 to the k plus 1. So right away, you can conclude that 2 to the power of a must be 4. Because if you prime factorize 964, it's 2 to the power of 2. And these cancel out. Now, there isn't really anything better to do here other than testing values of k. Each value of k you test, it's only going to take like 15 seconds. So it's not like too time consuming. And based on the answer choices, clearly you don't have to test like values of k that are like too high. So it's like feasible. So you can test like k equals 0, 241 times 2 to the 0 plus 1 is not 1 more than the power of 2, right? Because the right hand side is 2 to something plus 1, so it must be 1 more than the power of 2. K equals 1. That's 241 times 3, which is also not 1 more than the power of 2. You can go on until you get a k equals 4. You get that 241 times 17 is equal to 4,097, which is equal to 2 to the power of 12 plus 1. So right away, you can assign 241 to this. You can assign 2 to the power of k plus 1 into as this, and you can assign 2 to the power of m plus 1 k. So here you know that k equals 4. And that means m plus 1 times k is 12, so m is equal to 2. And above, we have concluded that a is equal to 2. So that means a plus k plus m is 2 plus 4 plus 2, which is 8. All right, let's move on to problem 22. So the main reason why people got stuck on this problem is because they tried to come up with some weird argument, or maybe even use calculus based on a. And I'll present a solution that doesn't really need any advanced techniques, and it'll make this problem very easy. So assume a is the largest number, all right? It doesn't matter which one's the largest number. Let's just assume a is the largest number. So that means a must be greater than 2b. So that means given that b is less than a, the chance that a is greater than 2b is so p of a greater than 2b, given that b is less than a, so a is greater than b, that's just equal to 1/2, right? Because for example, if a is 0.8, then b must be between 0 and 0.8, is given that a is greater than b, and the probability that a is greater than 2b is just 1/2. And the probability that a is greater than 2c, given that a is greater than c, is also 1/2. And you can just multiply these together to get 1/4. So really, you just gotta come up with this. There isn't really any other way or easier solution. Some people try to bash this using calculus, but that's very time consuming. Overall, this problem is kind of weird. So basically, you just simplify it by assuming a is the maximum and then go on from there. Okay, question 23. Basically, this question, you just got to come up with a combinatorial argument to find an expression for how many fair positive integers are there. All right? So notice you can't use zeros, so you only have the digits 1, 2, 3 until 9 for your disposal. Let's assume a fair positive integer has n digits. Then there are 9 choose n ways to choose those n digits from the available digits. And because it must be fair, you can't have if you draw the digits out. So for example, if you have 2, 1, 3, 4, it's 2, 1, 3, 4. This is not fair because 2 is greater than 1 and 3 is greater than 1. So you can't sort of have these valleys. So it must be so if the number is fair, it must be something like this, right? So you have the largest number here. And then for the rest of the n-1 numbers, you can either put them on the left or put them on the right. And for example, if you pick 1, 3, 4, 7, 9, then 9 must be the largest, so 9 must be in the middle. And 1, 3, 4, 7, you can either choose to put them on the left or put them on the right. So let's say you put 1 and 4 on the left, right? Then it must be 4, 1, because it must be in order. And like if you put 3 and 7 on the right, it must be 7 and 3. So this is the only fair like number if you put 1 and 4 on the left, given like that you're using these digits. So the number of ways that if you use those n digits, there's two possible like places to put the digits, right? Either you like build the number on the left, or you build the number on the right. And there's n minus 1 more like digits to choose from, so that's just 2 to the power of n minus 1. And obviously n can be anything, so you take the sum from n equals 1, because n can't equal to 0, and n is like less than or equal to 9, right? That's kind of obvious because there are only 9 digits. So this is equal to, so notice you can use the binomial theorem to get that 1 plus 2 to the power of 9 is equal to sum from n equals 0 to 9 of 9 choose n times 2 to the power of n. So that means this divided by 2 is just this time, it's just 1 less power of n. So this is just equal to sum from n equals 0 to 9 of 9 choose n times 2 to the power of n minus 1 minus 9 choose 0 times 2 to the power of negative 1. Because this includes n equals 0, but this doesn't include n equals 0. It starts at n equals 1, so you just subtract the n equals 0 case to get this. So this is equal to 1 plus 2 to the power of 9 over 2 minus 9 choose 0 times 2 to the power of negative 1. That's just 0.5. And then now you have like the answer, right? So you can manually compute this out to get that the answer is C. All right, let's move on to problem 24. Now, I'm sure everyone who got this far would have solved problem 24. All right, this problem is way misplaced. It should have been in like problem 15. So you can look at this triangle, right? So this is 1, this is 1. That means this is equal to 2. And this is r plus 1. And this is r plus 1. And this is 1/12 of 360 degrees, which is 30 degrees. So now you can use the cosine law to get an expression for 2 based on r. So you can just write out the cosine law. So r plus 1 squared plus r plus 1 squared minus 2 times r plus 1 cosine 30 degrees is equal to 2 squared, right? So there really isn't any like other tactics, like any like special tricks here. So this problem is like pretty easy. And if you expand it all out, you'll get a quadratic upon r. And then you can either factor it or use the quadratic formula, etc. And you'll see that r is equal to root 6 plus root 2 minus 1. So I don't think there is like any further explanation needed. This problem is like, yeah, after you like find out this triangle and use the cosine law, anyone can like very easily find r. So what is a plus b plus c? So this is 6, 2, 1. Add them up. Sorry, this c is negative 1 because it's plus c. So 6, 2, negative 1, add them up, you get 7. So the answer is C. Finally, with problem 25. So I know that this problem, there has been some discussion going on in the forums. This problem has actually had a mistake that MAA has made. So what I'm going to do, I'm going to present and discuss the solution that like MAA intended us to find, and then I'm going to explain why it's wrong. So the actual answer is 8, but that's like not an answer choice, right? So the intended answer is 13. I'll explain why, and then I'll like explain why it's wrong. So we have these two functions, right? And they need to like switch signs at A, B, C, and D. So notice rational function will switch signs if like at like k, if k is a root of p of x and k is a root, or k is a root of q of x, and k is not a whole. All right. So we have 6 like roots of either p of x and q of x, and we need 4. So that means exactly like 2 of them must be like the same, so they must be like a whole, right? So we can basically just case work on which like root is the same. So case, let's just say case 1, p of x is divisible by x minus 1, so p of 1 is 0. And q of 1 is 0. Now that means a must be 2, b must be 3, c must be 4, and d must be 5, right? So there's one solution. There isn't any other solution because a, b, c, and d are like all like less than each other, and a can't not be 1 because it's like a square bracket, right? So a must be like a solution. It can't be like canceled. Now we can do case 2. So p of 2 is 0 and q of 2 is 0. And you can do the same checking to see that there's no solution. And you can do case 3, where p of 3 is 0 and q of 3 is 0. So you can see that there's the solutions a, b, and c, and d is equal to, you can make it 1, 2, 3, 4, or 1, 2, 3, 5. Notice c or d can be like 3. It can be at the whole, because if it's an open interval, you're like, you have all the right to exclude c and d from like the domain, right? So another solution is 1, 2, 4, 5. And case 4 is where p of 4 is equal to 0 and q of 4 is equal to 0. Same thing here, right? 1, 2, 3, 4, or 1, 2, 3, 1, 2, 4, 5. And you can basically just like, and so on, right? You can basically just like continue doing this casework, and I'll just like list out the solutions for the case 5. Oh, here there's also 1, 3, 4, 5. So for case 5, it can be 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 4, 1, 2, 4, 5, 1, 3, 4, 5, and 2, 3, 4, 5. So in total, we've already found 13 solutions. Oh, and include this one. So in total, we found 13 solutions already, and 13 is the biggest answer choice. That means 13 must be the answer, because it's like, it's impossible for there to be more solutions, because like 13 is already the largest answer choice, right? And one can also easily rigorously verify that there's no like other answers. So that was the intended solution by MAA. And the reason why this is wrong is because sometimes we have the exact same function. And in fact, this happens exactly 5 times. So if like K and K was like the whole, and then it was like something else, it was like X, Y, Z, W. And then you have like K2, K2, and then is like any variables. So for example, like I, J, K, L. It just happens that 5 times these like the numbers on the top are the exact same as the numbers on the top here, and the numbers on the bottom are the exact same as the number on the bottom here. So this is like P of X, and this is like Q of X, right? And this is like P2 of X, and this is like Q2 of X. It happens 5 times, so we've actually overcounted by 5. So that means the actual answer is 8. But like, that's not an answer choice. So I think if you were to like get this on an actual contest, don't just like choose no answer. I think it's best to still choose 13 because they'll probably just give you the marks like anyway if you like put 13, right? It's like there's nothing to lose really if you put like the MAA intended answer. So let's hope that these types of mistakes don't happen like again. So here, if you want to screenshot my answer, all right. So yeah, that is all of the final 5 questions on the AMC 12 solved, and I hope you guys found the explanations clear. If you have any questions, you can post them in the comment section, and I recommend you guys check out our team's explanations of this year's COMC. And we are one of the only places where you can find the COMC solutions as of now. All right. So if you're still like here on this video, thank you for watching. Have a good night or have a good day. So this is the end of the video.